Okay, hi everybody. How's everyone going? Thumbs up, thumbs down. Too tired to make any gestures? um, so, how's everyone going with the linked list assignment? Hands up who's started it. Okay, so a lot of people here have started it, which is great. There's still probably plenty of people who haven't started it, but definitely try and start it soon. Don't leave it to the last minute. If you haven't started it because you just don't know where to start, that's a perfect reason to go to a help session. Okay, so, or if you're stuck on it in any way, don't hesitate to go to a help session. Ask your tutor in the lab. Don't just sort of wait until the last minute and keep panicking about it. Just get help. Hopefully today we'll help you with linked lists a little bit more. Hopefully, how are your labs last week? Did they help you get on top of the linked list material a bit, or were they really hard, easy? Not sure, still finishing them? Okay, hang on, I'll turn this down, I can hear myself too loudly. Okay, all right, well, let's get started. So, as always, we've got access to the code. Assignment 1 marks. So you'll get those out later today, probably this afternoon. You'll get a message on the forum telling you about it, and it'll tell you how to get the feedback and stuff. But don't just look at the mark, look at the feedback. You'll see what auto marking tests you passed and failed, which is different to the auto tests, right? You get auto tests that you see when you're developing your program. We run it on extra tests as well when we mark it. So it's important to look at that to see, to learn from it, and also read the feedback from the tutor about style, because that might be relevant to assignment 2, some of the feedback you get. So don't just look at the mark, just be aware that there's a way to look at feedback. If you can't work out how to do it, again, ask your tutor. I just want people to know there is feedback, not just the mark. All right, revision sessions. The next revision session will be in week 11, and it'll be like an exam revision session. So keep an eye out for that, sign up, vote for your favorite topics or your least favorite topics maybe that you need to work on, I don't know, and turn up to it too. Lots of people sign up for these revision sessions and then don't come on the day. That's all right, things happen, but try and come for your own sake. Oh, and another thing, somebody asked me about my experience. So my experience are just surveys. They're anonymous. It's nothing to do with your grade. You can just give feedback about the course, okay? So you don't have to worry about my experience in terms of don't be scared that you're gonna, lose marks or something. It's anonymous, it's just feedback. We do hope everyone does it, but it's nothing for you to be scared about. And another thing that's nothing to be scared about is we've got a practice exam next week in the lab. It's how you get your lab marks, but again, you've just got to turn up, attempt at least one sort of solution and submit it to get those marks. And it's just another chance to make sure you're really comfortable with that exam environment. So on the day of the actual exam, you don't even have to think about that. And it's also a chance to do maybe a linked list hurdle or two in an exam sort of situation, right? So it'll run for 2 hours. If you want to, you don't have to do it for the whole 2 hours if you like, but I definitely recommend trying a few questions. If you then want to log out of the exam and work on your assignment, that's fine, or you need to do something else, that's fine. But I recommend at least trying a few questions in the exam environment, especially a linked list hurdle. The other thing is, if you do sit there for the whole 2 hours and try and do it, just realize that this is a sample exam that is meant to be done in 3 hours. So if you get to the end of 2 hours and you think, oh my goodness, I didn't even nearly finish, well, that's right. I don't think anyone would be able to finish it in 2 hours, really. I don't know many people that would be able to. So that's completely normal. Just be aware it's a 3-hour exam. You're sitting there probably in less than 2 hours by the time you get to the lab and stuff like that. So don't let that sort of panic you either. All right, and if you're in an online tute lab or for some reason you can't make it to your regular one, you can try and sign up for an in-person lab for week 10. So that's week 10, not this week, just letting you know in advance. Does anyone have any questions about any kind of admin stuff for the course? Any of what I've just said? Has everyone seen the date of the exam yet? We all know when our exam is now, don't we? In the lectures tomorrow, we'll talk more about the exam and how it's run and just exam information. But yeah, we'll do that tomorrow. Okay, how are people going with inserting nodes into linked lists? Smile if you're doing well. Pretend to cry if you're not doing well. Okay, what about deleting nodes? We've only just done that. We're going to recap that today. And then we're going to do an application where we're going through, traversals, which means just looking through them, inserting things into linked lists, but with sort of more complicated data, sort of closer to the sorts of things you're going to do in the assignment rather than just a standalone linked list with integers. So hopefully this will help you a bit today. Let's see. This is just a little exercise to remind us of, because you're probably seeing lots of boxes and arrows everywhere when people are explaining linked lists to you. At some point, people either forget what those boxes and arrows really mean, or they never understood what they really mean. How's everyone going with the boxes and arrows? Do we know what they mean? Or is it a bit confusing? I've got some thumbs up. Anyway, let's just go through some of the basics before we recap deletion. Because linked lists do take a bit of time. If you're finding them difficult, you're not the first person in the world to find them difficult. I don't know really many people that saw them for the first time and didn't think they were difficult. And I remember being completely confused. I kept seeing all these boxes and thinking, I get that, but what's that got to do with the code that I'm writing? Anyway, so if I've got, remember, this is what our nodes look like. And in an application, they might not be called node, right? So in the assignment, you've got linked lists. They can't all be called struct node. Some of them are like, what are some examples in the assignment? Struct song, struct stage. I don't want to say the wrong words. And then they're going to have some data. In this one, we've just got integer data to make it simple. Obviously, in real world applications, you've got maybe lots of data, strings, ints, other linked lists, all right? But all of the basic logic should still apply. And the other key is you're going to have a pointer to the same type of struct. That's the field that connects it all up and makes it a linked list. And often it's called next, but even if it wasn't called next, or even if you had a different field called next, the key is that you've got this pointer to a node of the same type, so you can link these things together. All right, so in this situation, I've got a variable. What type is my sort of head variable? Yep. Yeah, it's an address. It's a pointer. So this head that we usually have is just a pointer. A pointer variable stores an address. This type of pointer variable is meant to store an address of a struct node. And in this example, it does. So I've got these sort of, fake addresses I've made up of where these nodes are living. And these are just mallocked chunks of memory living somewhere in the heap. And let's just imagine these are their addresses. And head literally is just storing the address of this first node. And that's how we know where the linked list starts. And then each node knows the address of the next node. and we draw this with arrows, right? And that's how we're linked together. Then the last one's null. Is everyone sort of happy with these basics? All right, so everyone call out loud. If I've got my variable and it's called head, how do I print out the data in the first node, or how do I access it? So the data in the first node is %d because it's an int, but how do I access it? Anyone? Yeah? Yeah, head arrow data. Except I didn't draw an arrow. I said arrow, but I didn't draw it. Head arrow data. So remember, if I've got a pointer to a struct, to access any of these fields or members, whatever we call them, you use arrow instead of dot. So head arrow data would give me this 13. We've got chocolate throwing happening here. How would I print out this address? Not that I typically want to print it out, but how would I print out this address? It is actually an address, so we'd use %p, which is not that important. But what would I write? Yeah? Oh, not the address of this, the address stored in this node. Yeah, head, that's right, there's lots of addresses here. I wasn't very clear about which one. Head arrow next. So when I've got a pointer to this node, I can use arrow to get the data. I can use arrow to get the address out. And this address tells us where the next node is. Everyone happy with that? Okay. What if I wanted to print out the data in the second node? And forget the printf %d, how do I just access that data? So I could say head. So head next gives me a pointer to this node. And when I've got a pointer to a node, I can access its field. So I could then say arrow next. Oh, but I don't want to do arrow next. I want to do arrow data. So yeah, if I've got head next, that gives me a pointer to this whole node. I can say arrow data. Is everyone sort of happy with that? All right. Now this isn't something I suggest you do, but this might be something you accidentally do. How could I modify the next field in the first node to be null? So I say head arrow next, and this time I'm like changing the contents of that. So right now it has the address of the next node. If I set this to be null, which is a very bad idea, what does this mean? What's happened to my list now? Yeah, there's only one node in it. I've lost the rest of the list. Even if I wanted to do that for some reason, what's the problem with this? Yeah, I'm going to have memory leaks. So once I overwrite one of these addresses, I've lost the rest of the list potentially, if I haven't stored it anywhere. So it's like if you've got your friend's address and you scribble it out, you don't know your friend's address anymore unless you've memorized it. And you can't just go around knocking on all the doors in like Sydney or something to find them. All right, just checking we all know what the diagrams and arrows and fields are doing. All right, let's do a recap of deletion. So we've seen like last week, whether we're doing insertion or deletion, one of the cases that we're always thinking about, hopefully, is what about if we've got like nothing in our list, an empty list. So if I've got an empty list, my variable head, or whatever it's called, will have the value null in there, which means no address. And what happens if you try and dereference that address, or go to that address and get data out from there? So if I try and say head arrow data or anything like that, head arrow next, and my head has the value null in it, what happens? Yep. Yeah, it's an error, and my program probably crashes. Absolutely. So we don't want to do that. So we've always got to check, well, not always, but depending on what we're doing, we might need to check, well, I'm trying to delete something from this node and I'm doing all this stuff. Is that going to break if my list has nothing in it? So if I've got a list with nothing in it, can I delete the first element? No, there's nothing to delete. So we've got to make sure if we're deleting the first element in a node, we check, do we have any nodes? Is the head of the list null? We might write it, is the head of the list not null? But we've got to check for that case. But otherwise, let's assume our list is not empty and we do want to delete a node. The idea is we don't want head pointing to this first node anymore because we're going to delete it. We want it pointing to this second node. How would we do that? Just say I did want to make it point here, even though it's a bit unwise right at this stage. What am I actually going to write in code? Sorry? Who said that? Someone said, I think, something good. So I'm changing where head's pointing. So in this example, I don't want it to point to 28 anymore. I want it to point to address 80, or in other words, this node here. I've got to change what head is pointing to, or the address that it stores. Where am I going to get this address from? Yeah, head next. So this would indeed change this pointer to point to this second node. What's wrong with what we've done though? Yep. You what? Yeah, so now we can't free this. We've got no pointer to this node anymore. We've destroyed that address. The only address that had that, the only place that address was stored was in head. We've lost it. So we'd now end up with a memory leak because we can't free that node. Any questions about that? Okay. So we do have to do that, but not just yet. Now, what if we freed this first? We do want to free this node, but what if we free this first and we haven't moved head to here? Yeah, we've lost the second node's address because we've freed this chunk of memory. And if we forget that and still try and access it, this will crash and it'll say you're trying to access freed memory because this address lives here in this node that we've freed. So we can't do that. So we ended up with this situation where we couldn't do either of the two things we wanted to. We needed to create a temporary variable. I've already gone through that case. So what we can do, this is just one way to solve this. I can just have another pointer pointing to this first node. So I can just say temporary equals head. They're both pointing to this first node. I can now move my head pointer to point to the second node, but I've still got a pointer that has the address of this first node. I haven't lost it. So then I can call free. And we've often got to do things like this with linked lists. We just have to make sure we've got all the addresses we need and we're not overwriting anything we need and we're not accessing anything we freed. Any questions about this? So we did do this last week. So I think I went over it probably in a slightly different way. Different ways will make more sense to different people. And we've coded it up and we tested it. We also wrote this delete all nodes. I won't explain this again right now. It has similar issues to what we just saw, and we'll be doing this later in our linked list application. The other thing we looked at was search and delete, and that was really starting to get quite tricky. And I'll show you a second way to do it. So when we wrote search and delete, we were searching for a node in the list with a particular value in it, and then we were wanting to delete it. And it has a lot of different sort of cases or situations you want to consider. So yeah, like always, we would probably want to check, does the code we write work if there's nothing in the list? If there's nothing in the list, you can't find anything or delete anything. What if the list isn't empty, but it doesn't have the value you're looking for? Again, that's another situation where, okay, you can search through the list, but you can't really delete anything, right, if you didn't find it. Perhaps the node you're trying to delete, you find that value in the first node or the head. Perhaps it's somewhere in between two nodes. Perhaps it's at the tail. You know, we tested to check that our code worked in all those situations, and at first it didn't, and we debugged it. We've just assumed for now that we're not deleting all the occurrences. So if we're searching for 42, we find the first 42 and delete that. We don't keep looking and deleting any more 42s. But we will look at that later today or tomorrow. So when we're trying to delete something, we need to sort of find the thing we want to delete, but we need a pointer to the node before it in order to delete it. So if I want to delete 42, that's great. But if I only have a pointer to this node, I can't really go backwards. And I need to make sure this node before it connects to the one after it. So I kind of need, as I go along, to somehow have a pointer to this node before the one I'm going to delete. So last week, I did it one way. I had 2 pointers. I won't go through that right now. I want to go through it a different way with 1 pointer, but always looking at current next, because it just shows you 2 different approaches that might come in handy in different situations. And then we'll try and debug this one as well, because hands up who has already got lots of bug, like have you had your program crashing and stuff with assignment 2? It happens, it's gonna happen. Even when you, like if you've been doing linked lists for ages, you're still gonna make typos or sort of forget to do something. You're still gonna have bugs. All right. Sometimes even when I've got it on the slide and I type it in from the slide, I've got bugs, so. All right. So let's just explain this for the general case. Then we'll run it with the test that we wrote last week and just see what breaks. Obviously, if we notice anything could break, we'll try and fix it first. So in this implementation, we're making current, oh no. Okay, we managed to silence the phone. Anyway, sorry. We make current point to the head. And what we're always doing is we're always looking at the next node. So we're checking, well, is this next node null? No. Does the next node contain data that's the data we're looking for? Let's assume we're looking for 42. No. So we move current along to the next node by saying current equals current next. So current's here. And then we do this again. Is the next node null? No, this is a node. Does it have the data I'm looking for? Yes, I'm looking for 42, and now I know that it's in the next node. So now my loop is going to stop, and I've ended up with this pointer to the node before it, which is exactly what I want. Is everyone sort of happy to there? And then we know, well, I want to somehow connect this to here, and free this. But I end up with a situation like before where I can't free it first, because then I can't access this next node. And I can't change this pointer to point to here, because then I can't free this node. So again, we can just create another pointer that stores the address of that node we want to delete. Sort of said that like this, right? Create a temporary node. In this case, we're making it equal to current next, because current, the one after current, is the one we want to delete. And you don't have to call it temporary. Then we can connect current up to the next node. What would that look like in code? We're changing current next. We don't want current next to point where it's pointing. What would the code be in this situation? Yeah, we can say temporary next, right? So temporary is pointing to this node. This one here is the next one after temporary. So I can say, well, current next isn't temporary anymore. It's the one after temporary. Is there another way I could say it? I can hear people going, next, next. Yeah, you could say current next equals current next, next. Whichever way is less confusing for you is the way you should do it, because it's going to be the same thing. Because this is current next, and if you go to the next one after current next, you get to this one, current next, next. You can say that. So that's what we're going to do. And I've already coded up this while loop that goes through and is checking whether the next one's null and checking the data inside it. And I'm going to call it temp instead of temporary. And remember, temporary is going to be the one after current. So it's equal to current next. Can everyone hear that something sounds like a hairdryer or a flight taking off? Okay, good. I don't know if it's my laptop. Okay, what do I do next? We did look at it on the slide. I can say current next equals temp next. Is that right? You should always have a diagram. And then what do we want to do? So I've done this. What's the last thing left to do? Free temp. Okay. Now, oh good, it stopped. Now, can anyone, so that's sort of, we've looked at that general case. Is there any code that you're looking at that's screaming out at you, oh no, that doesn't look good. What are we going to do here? Yep. The tail? Can we remove the last one? We do have to think about something like this, but just imagine, so I definitely need something like this. Oh, so are you saying if we wanted to remove the 5? If we want to remove the 5, that should be okay, because what we'll be doing is saying, we'll stop there. We'll say temp is current next, and then we'll say current next equals temp next, which is null. So that's going to be okay. If we say something like current next equals null, that's legal. If I say current next and current is null, so I'm in effect doing null next, that's going to be a problem. So that should work. What other cases are there? Yep. The beginning. Can anyone see what's wrong with the code if I was trying to delete 13, for example? Let's have a look. So when I originally start, I have current pointing to this node here. What's the first node that I check the data inside of? Yeah, so I look here at the 17 and I go, is that 13? No. I move current along. Is that 13? No. I move current along. Is that 13? No. No, I didn't find 13 in the list. So the way we've written it right now, it's not going to work when we try and delete the first thing in the list. And there's also something else in here that should be screaming at us anytime we see it to say, uh-oh, please look at this. I've got this here. Why is that a problem? When list's empty. Exactly. Oh, that's excellent. Somebody give him a chocolate. He's made screenshots with his answer. Awesome. Yeah, what's going to happen if the head of the list is null, right, because it's empty? Car will be null. And then we're saying car next. We're going to be crashing our program if it's empty. So we've got all these cases to consider actually. And there's probably one more. But what I'll do is, the first case is quite easy to handle. So if head equals null, I don't want to do anything. So I'm only going to do all this stuff if head is not equal to null. Right? So if head's not equal to null, yeah, I'll search through and I'll try and delete something. If head is equal to null, I'm just going to return the list as it is. So this is something you can commonly do, wrap everything up that you are doing inside a condition like this. Please don't do this. Only do this if it's not null. What are the other things we said were wrong? Well, let's actually see these errors in action. Oh, I'm not in the right directory. What have I done? Oh, I've called it car. To save me typing 3 characters. Okay, so it compiles. And remember, I've got this main that's just trying to test this function really. It does try to search and delete from an empty list. Then it adds some nodes to our list. Then it tries all sorts of different scenarios. Okay, so it's crashed. But let's see where we got up to. So it was able to search and delete from an empty list, and we still have an empty list. That's because of that condition we just added. That would have crashed otherwise. Then we had a list with all of these numbers in there, and we searched and tried to delete 4, and that was somewhere in the middle of the list between 2 nodes, and it looked like that worked. We deleted 4, that's great. That was the case that we really thought about in the slides as well, right? What about when we try and search and delete 99? Crashes. So what's this case? This is the case where the thing that you're searching for does not exist in the list. What's happened here? It's going to tell us what line it crashed on. And it's going to tell us, well, temp was null. And you were doing this. So in this particular way we're doing it, let me just imagine that we are looking for 99. Well, it's never going to find it, and it's going to stop the loop when we get to here, right? Because current next is null. So it'll stop here. And then without thinking about whether we found it or not, we just start going current, equals temp next and all whatever sort of stuff, and that crashes it. So we've got to think about it, or temp equals current next, sorry. If our temp is null, we didn't find anything to delete, right? If the one after current is null, we didn't find anything to delete. We've got to be careful. So down in our code, where is it? Yeah, we've got this temp variable. We probably need to say, well, actually, if temp is equal to null, what do we want to do? Nothing, right? If temp was null, we didn't find the node, we don't really want to do anything. So we can just make sure that we only do it if temp is not equal to null. So that means if we did find a node to delete, then we go and do this stuff. If temp was null, we didn't find the value, do nothing, just you'll end up returning the list as it is. So we'll need something like that. Let's try this again. And we still haven't solved, we know that it's not going to work if we delete the first element in the list. Okay. So we were up to here, we were trying to delete 99 and it was crashing. Now it's not, it's just leaving it the way it was, which is good. We try and delete the last node and that worked, which is good. We try and delete the first node, it didn't work, it's still there. We had worked that out. Someone had suggested that. How do we fix that though? It's working beautifully unless we want to delete the first node. Does that mean this is just a terrible solution and we should get rid of it and start again? Yeah?
We can add a condition if current
next, this one is, that's what we did for temp to fix that. How do we work out if the first one in the list is what we're trying to delete? So yeah, we can either just call it head. There's different ways, always different ways to do it. So if head, we've already checked head's not null. So if head data is equal to the thing I'm interested in, then I'm basically deleting the first node in the list, which we've seen before today. Otherwise, and everyone will have different ways of doing this, there's no exact way. Otherwise, then we go through this whole process of looking through the whole list. But we've now got a case, I found it at the beginning. We basically can say something like struct node temp equals head, head equals head next. We just went through this before, deleting the first node, and free temp. Is that right? Basically what we did to delete the first node from a list. Is this going to work? Yeah, so now this case works and the rest still work, I think. So look, depending on how you actually code things up, you might have different sort of bugs for these different cases, right? When we implemented it last week a different way, we had a lot of bugs, but they weren't exactly the same bugs, right? So this is just an example of things that can pop up when you're doing your linked list coding. Any questions about that? Yeah?
I have a question. Do you have a preference for which one we can use? Because we did previous and current.
I don't care. Yeah, look at the other one. Whichever one makes more sense to you, use. And if you're in a situation where this might be relevant, just whatever you think is easier and nicer. It doesn't matter. They're both relevant ways. I tend to like using prev. I don't know why. Maybe that's the first way I was shown. And once you start using current next and next and stuff, I don't know. But it really doesn't matter. Which one seems easier to you or makes more sense, just use it. Okay. So yeah, we're getting into tricky code here. We won't do the delete all occurrences right now. Now we've got a little bit of time before we go on our break. So I'll just start introducing this thing we're going to do in the next half of the lecture. Are we ready, or is our brains just scrambled from the deletion? Okay, let somebody put their thumbs up, so I'm going to start. All right, this is an email management system, and obviously it's just a very sort of toy example. We can't write a whole proper email system here in an hour. And like the assignment, we've got 4 files, kind of like the assignment, but yeah, we've got a .c file where we've got to go and implement some functions, and there are some provided in there as well. We've got our email management system.h file that has hash defines, enums, structs, prototypes. We've got 2 different mains. We've got a main that's sort of an application, an email application that does something slightly useful, kind of. But then we've just got a test main as well. And that's sort of got the sort of code we just wrote in the main for search and delete. That was like what you'd think of as a test main. It wasn't doing, it's not a program you're going to sell to anybody. It was just checking that that deletion worked. So we've got a file here that just checking if all of our functions work, whereas main.c is using them in a useful way. And yeah, I believe you do have in assignment 2, you've got sort of a test main given to you to test some of your earlier stage work. And basically what we're doing is, yeah, we're implementing the functions in the email management system. So before you ever start coding, whether it's an assignment, whether it's an exam question, just be careful you know what you're doing. Well, not know what you're doing, but you know what you're trying to achieve, right? What you're being asked to do. And you want to know how it fits together. So if you've got a number of structs, you want to know what's going on with those structs and have a good idea before you just start coding. You even need to make sure, if you've got multiple files, that you know how to compile it all, hopefully. And you maybe draw some diagrams to see how all the structs fit together. Draw diagrams when you're coding your linked lists. Does anyone do their linked list coding without drawing diagrams? Do you have like awesome diagrams in your head kind of thing? Or you just, yeah, I don't know. I like having a diagram. All right. So in this example, we've got struct folder, and it's only got 2 fields at the moment. There's a 3rd field we might add for later. We probably won't actually get up to it. And we've got struct email. So there's nothing called struct node. There's nothing called head of the list. What's our node in this example though? What's our linked list node? So which struct is going to make up the nodes in the linked list? Yeah? Folder. So to have, yep. Yeah, email, struct email. So folder actually contains a member or a field that is a linked list, but struct email are the nodes. How do we know this? Well, because I made it up, but also struct email has a pointer to another struct email. That's the thing that you have to have for this to be some kind of linked list node. And you'll see in the assignment as well, your struct song, for example, is going to have another pointer to a struct song in there. And we often call these fields next, but even if it wasn't, you know, that could still be a linked list node. Then all of the rest of this stuff is the data we're storing in this node. This struct folder has something that has a pointer to struct emails, what's this equivalent to? This field here. So this is basically the head of the list. So we've been in lectures, we've looked at sort of standalone linked lists of integers, and we've had just a standalone variable that's a pointer, and we've called it head, and it's been very obvious that that's the pointer to the beginning of the list. Here it's buried in this other struct. Okay, and it's these things that then add a layer of confusion if you're just getting started with linked lists, because you think, well, there's just structs and all this data, I don't know what the linked list is or how to access the first node. But yeah, it's this field in this folder. Yep.
Is folder also a linked list or not?
Folder's not a linked list in itself because there's no field that has a pointer to a struct folder, right? This has a pointer to the same type.
So what is the pointer in folder pointer?
So this pointer, I'll draw it, I'll show you in a second. So this is the head of a list of emails. So in this example, where's my mouse? Oh, here it is. In this example, I should have gotten rid of this field from the drawing. We've got folders, and a folder's a struct, and a folder has a name, and it's basically got a linked list of emails in there. And at the beginning, it'll have null because there's no emails. So this is basically like when we've got head equals null or something. It's just that the head of this linked list is stored in this folder. Once we've then added some emails to our folder, we get something like this. So this folder is a struct, but it's not a node in our list. These are the nodes. They point to, you know, next, next, next. This is just a struct that happens to have the pointer to the first node in there. Does that make sense? So basically we've got a linked list of struct emails, right? And we can have many of these nodes, they're all connected together. Struct folder is basically like a container sort of that points to this linked list. So we could get rid of this folder and not even have it. And I could say struct email star head, and you know, just point it and have a linked list like this of these emails. But instead of doing that, we're putting this head field inside this other struct. So now a folder has a name, and it also has a linked list of emails that it knows where the head of those emails are. Does that kind of make sense? And it's this kind of thing that you've got in the assignment. Your linked lists are sort of buried in these other structs. These other structs will have the head of the linked list in them. And the linked list will have struct songs or struct whatever's in them. Okay. Any more questions about that? Because this is the sort of hardest thing in terms of understanding how it all fits together. Okay. So let's have a break. When we come back from the break, we'll start coding this up. And the first thing we'll do is create a folder. And that's going to be similar to the sorts of stuff you'd be doing in the assignment stage 1.1. Some of you might have already done it, but hopefully that'll help people if you haven't done it yet. And then we'll insert emails and search. We might not get through anything else today, but let's come back at about 5 past. Yep, okay. So let's start coding this stuff up. So we've got our .h file, and it's got hash defines. It's got some enums that we'll look into once they're more relevant, but email types, priority types. It's got the structs that we looked at in the slides, our struct folder that contains the head of a list of, struct emails. And then it's got a whole bunch of prototypes. Then in this C file, that hash includes the .h file, but in this C file, there's functions that we have to implement. There's some that have already been done already, to print an email. There's a few bits and pieces that have already been done. Then we've got a main program. Oops, didn't mean to do that. We've got a main program that when it runs, you can add an email and print an email and all sorts of things. And then we've got the other main that just goes through and is just calling all these functions, and we can look at it and see if it's working, sort of like what you've been given in the assignment at some point. How do we compile all these things together? Well, we can use DCC. Now, I can only have one main function at a time that I'm compiling, right? I can only have, each executable only has one main function. So just say I wanted to run this test main. Oops. I'm in the wrong directory. Oh, that's not the right one either. Okay. Now I can't just compile it like this because it's going to say, hang on, you're using all these functions and there's no code for these functions. So we have to compile the C file that has the main in it and all of our other C files that we're using that don't have mains in them together. And that creates one executable that we can run. And right now, it doesn't do much except print out that we haven't done this yet. If I tried to compile the other code that has another main function in it, the compiler is going to complain and say there's multiple main functions that you're trying to compile together. It's not going to work. Does that make sense? Now, if I wanted to compile and run the other program, then I would use that one instead of test main. Right? So I can create two different programs here. And again, this one doesn't do much yet either, okay, because we haven't written any code in the functions. All right. So the first function that we want to write is the function to create a folder. I just tried to do clear. Oh, there we go. Just to create a folder, I'm going to delete all this stuff that says we haven't done it and exits the whole program. And we're given a string and we're supposed to return a pointer to a struct folder. Now, if I've got to return a pointer to a struct folder, where does this struct folder need to live? Can I do this struct folder f and then, add stuff to it and then return an address of this? Yeah, we can't return the address of a local variable. So this is why if we're going to have to create a folder and return an address of it, we're going to have to use malloc, exactly. So I'm going to call this new folder. So struct folder star, new folder. This is going to be a pointer to a folder struct that I'm going to malloc. If I want to malloc a struct folder, I ask for size of struct folder. I don't want to ask for the size of struct folder star. That would be asking for enough memory to store an address. I want the size of a struct folder that has enough memory to store, everything we need to store in a folder. So this step here is doing our malloc and giving us a chunk of memory. And in real life, if you have a job, you should, and you're coding in the job, make sure you check what malloc returns. Because if you run out of memory, malloc's going to return null. Now in the assignment and in the exams, we're not going to be strictly looking at that. So you can get away with it, but in real life, please check for null. All right, but what else do we have to do? Well, we're trying to create an empty folder that has a particular name. So we want to, I'm so sorry I didn't delete this from the picture. We just want to set all the fields in here. We've done the malloc, we've got the chunk of memory. We have to make sure we initialize our field that's called name and also our other field called emails. We should make sure every single field in that struct has some sort of initial value. Otherwise, as the rest of the program starts using that struct, what happens if you've got things that haven't been initialized and you try and access them? In C, or with DCC, it's going to crash and say you're accessing uninitialized memory. So that's our job. We've done the malloc. We need to initialize all of the different fields inside this struct. And if we just remind ourselves what's in the struct, we've got a name, which is a string, and this basically linked list of emails, but it's just a pointer, right, to the first node. So I've been given a name. Get rid of my scribble. I've been given a name for a folder, so maybe you've got a folder called uni or something in your email. I don't know, maybe you don't. We're going to, we're trying to put that name, whatever the name of the folder is, into the struct. And the name of the input to the function is called name. The name of the member or field in this struct is also called name. So we've got a pointer to this struct. To access the fields inside it, we use arrow. And what you're kind of probably going to want to do is something like this. Say new folder name equals name, right? We're putting the name that we got from input into this struct. And that's conceptually what we want to do, but what's wrong with this in code in C if these are strings? This is like an array, and we're kind of trying to make an array equal to something, right? What do we use instead of equals when we're dealing with strings like this? Yeah, string copy. So that's right. So instead of using equals, we're going to use string copy. So don't forget that. Now again, if you've got a job and you're writing code, what might be a problem here? So, where's my mouse? This is not an infinite length array. This has max length 100. So if your user's trying to type in some really long name for their folder with like 101 or even 100 characters, but too big, this string copy is going to overwrite memory and or crash. So in real life, you might just want to do the string length of that string first and check if it's too big, and maybe you only copy in part of it or something like that. I don't think you've got to check for this in the assignment though, do you? Your string copies. I don't think so. All right. So let's just assume for now that we know that this name is not going to be too big. In your job, don't assume anything. Assume that everyone's going to type the wrong stuff in all the time. What about our other field? So we've set name. What are we going to set for emails? They haven't told us what to set. They've told us what name to put in here. They haven't told us what value to give our emails. What's a sensible value to initialize a linked list to? Yeah, null. So we say new folder, emails equals null. So by the time we've done that, we've pretty much done this, right? We've created a folder, we've set the name, forget this field in the middle, and we've set our list to null. So that's our empty folder, we can return it. And yeah, this is the sort of stuff you are doing in assignment 1.1. Let's compile it. All right, let's see what I did. Oh, that was my bad example of how not to compile it. There we go. Okay, so let's run test main. Test main has created a folder. It says there's no emails in our empty folder. So there's already code that traverses the linked list that's saying there's no emails in there. Okay, so there's not much to see. We haven't done much code, but we've created an empty folder. Any questions? Now we want to insert something into a folder. So imagine I've got a folder. We've already got some emails in there. I want to insert an email into this list, and it's saying to insert it at the head. So I need to make a struct email and set all the relevant fields. And then I need to connect this email to this list at the beginning. So I'm going to set the next field in here to point to this, right? Does everyone agree? I want it at the beginning. And then what else do I have to do? So this field in here is keeping track of where the first email in the list is. We need to make sure we update that so it knows, oh no, this is the first one in the list now. Okay, everyone happy with that? Okay, how do we do that in code though? Well, first of all, we probably want to make a function that can create an email, and I'm going to keep calling it like an email node. And unfortunately, the tedious part is here it's got quite a few inputs. Let's bring this up here. And while I'm doing this, you can think about how we're going to connect it up. So this create email is similar to what we did before with create folder. Except there's a lot more fields. We're initializing every field in this. So we're just going to say struct email, new email, equals malloc, size of struct email. And that's going to give us our chunk of memory. Then we're just setting all these fields. So in our new email, we've got a field called sender, and we want to set that to the sender that's in the input. Of course, this is a string again, so I have to use string copy. Oops, what am I doing? There we go. And I've got to do this for all of them. So try and think about, once we make this, how are we going to connect it to our list? Size. copy. And for now, in this function, we don't really have to use our brain to think about what the next one will be. We're just connecting it up to whatever the input says for now. Is that everything? Did I leave anything out? 1, 2, 3, 4, 5. Okay, so I've got to create email. So when I'm inserting at the head, the first thing I'm going to do is create this email node. And I'm passing in again the sender, the subject, the size, whoops, the type, the priority, and I'm passing in what should come after it. Like I'm passing in the next field, which shows where we should connect it to. So we've got to think about what we're doing here. So let's just draw this. I've got some folder called email folder. It's got a name. I don't really care about the name. But it contains the head of this list of emails. And that field itself is called emails, but this is the head. It's inside email folder and it's called emails. Now I've just created a new node and I've filled it all in, but I want to tell it where to connect this next field to. So where does this field need to point to? We know it wants to point to here, but how do we say that in this code? So we want it to point to the head of the list, but we don't have a variable called head. Where's the head of our list? So what right now is pointing to the first node in the list? So this emails field is the thing that has the address of the first node in the list. So that is basically our head of the list. So if this is in a struct called email folder, how do I access this field? Email folder is correct. That email folder is the name of this folder, but what's the name of the field in here? Yeah, emails. So in my folder, I've got this emails field that stores an address, and it stores the address of the first node in the list. So this is the head of my list, right? It's a pointer to an email struct. So if we go back to maybe a nicer diagram, it's this field here that points to this first node, right? It's whatever the folder's called, arrow emails, that's the head. So, and I'll get rid of my yucky drawing. So once we've got this, we want this next one to point to the folder arrow emails. Then once we've added this here, we want this head of the list to change and point to this new node. Okay, so yeah, in here I've already done this. Let's make it a bit wider. I've said new node, put all this data in there and set the next one to what is currently the head of the list in my folder, because I want this node to come first and all the emails that are already in there to come after it. And it's getting too wide. Okay, that'll do. And now I've done that, I need to basically update the head of the list. And the head of the list is in this struct. So I say email folder emails equals this new node. Right? This is basically saying the head of the list equals this new node, conceptually. Now, with this, usually when we're adding something to a linked list and it might modify the head of the list, we've been returning it. So the variable back in the main function or wherever it is gets updated with that information that, oh no, this is the head of the list now. In this case, we don't have to do that because we've got a pointer to a struct that's still going to exist when this function ends that is keeping track of the head of the list, right? So this is us updating the head of the list here. We don't have to return it. We're updating it right here on this line. It's buried in a struct that's on the heap. It's not going to disappear when the function ends or anything like that. It's not a copy. We've got access to that original folder. Yep, question?
Yeah. For the creating a new email sort of function you did.
Oh, I called it create node. Hang on. Sorry. It should be called create email. I just keep typing node in all the time because I'm thinking of node. Sorry, I'll call that new email. I should call this new email as well. My hands are just automatically typing the word node. Yep.
When would you set the next node to null? In certain cases, when they create the function for the email, they set it to null.
Oh, when we're setting it to null, when we create our folder, we're setting the head of that list to be null. That would be an empty list. When we're creating a new node, the time you might set it to null is often if you're inserting it at the end of a list. Now, right now, people might be thinking, does this work if there's nothing in the list? Is that going to be okay? And yep, if there's nothing in the list so far, imagine I've got, let me just draw this situation, emails equals null. There's nothing in there yet. We'll make our new node. We'll connect new node to the head of the list, like we'll say the next one after that is null. That's fine. And then we say, actually, our emails list starts here. Oh dear. Oh dear. Our emails list starts here now. So if this was our email folder, it had nothing in it, we would be setting the next field in our new email to be null, because that's what email folder emails would have had. And then we're updating it. So now this would point to this new node, which would be the first one in the list. Does that make any sense at all? Any questions? And typically, if you're creating a new node and you know you're going to put it at the end of the list, you would always just set it to be null. All right, each may be what you were asking. Okay, actually, let's see if this worked. Oh, we've still got a bit of time. Now, unfortunately, sometimes when we're programming, it can take effort to see if something does work. We've got to see what the testing program was doing and just check it's right. So in our test program, we inserted 5 emails. Because we're inserting them at the head of the list, they're going to appear to be sort of in the backwards order. So we're expecting Tammy, Brianna, Tim, John. And it says we've got 5 emails. That all looks okay. Any questions? Are we ready to go and search through our list? Oh, I am seeing some thumbs up. Thank you. That's good. Now, in this particular example, we're searching through our emails in our particular folder, and we're searching for the subject. So we're trying to match a subject. So our emails all have strings. Let's imagine the subject here is, I don't know, maybe I should make different ones. B, but these are all strings, whatever is in there. Think of the subjects of your emails. I don't know, exam, week 8 lab tests, I don't know. Now, if we're searching through here, what we're going to do, typically when we search through a list, what do? We probably want to start at the first node and we check, is this what we're looking for? Imagine we're looking for the string B, and we'd say no. We move along, is the subject here equal to B? Yes. And we stop our loop and we found it. In this example and in lots of useful examples, we're not just returning yes or no, we did find it or we didn't find it. We're going to return a pointer to this node, right? Here's that email that has that subject. And then now you'll have access to everything else in that email as well. That's typically what we do when we search for things. Now imagine if we were searching in this case for some string, I don't know, let's just call it X. It's not going to find it. It's going to go through this whole list. It'll stop when it gets to null, and we never found it. What are we going to return if we didn't find something and we've got to return a pointer? Yeah, we just return null. So it's very common if you're searching for something and you find it, you return a pointer to that thing. If you don't find it, you return null. And anyone using your function is going to know that, and it's going to check and say, well, if it returned null, I know we did not find anything with that particular matching subject. Otherwise, we did, and here's all the data that you were looking for, kind of thing. So the first thing I really want to do, I'm going to do a while loop, and I'm going to set current to this first node. But how do I do that again? So I'm going to have like struct, and I'm probably going to be lazy and write car. Oh, hang on. I'll do it up here. Struct email car. Ugh. It's very different when you write to type. What am I going to write here to set it to the first one in the list? Yep.
Folder, arrow, email.
Yeah, folder, whatever the folder name is. Arrow emails. Yep, so we've got to get used to this sort of being the head of our list. This is like saying car equals head, but that head's buried in there. Yep, question?
What if the email doesn't exist? We're accessing null. How do you...
If the email, so if we return null at the end in our function and it doesn't exist, that's right, whoever uses this function is going to call search, and it's going to have to check if search, like if it returned whatever variable it's storing in, if that returns null, we better print out a message maybe to the, I don't know, like when you search on something, it'll say we didn't find it or no matches or something like that.
But you're saying folder, arrow, null.
Oh yeah, now that's going to be okay. So if car is null, and if we have a loop, it depends what our loop is doing though. It depends what our loop is doing. If we're saying car next in our loop, that's 100% going to crash if it's null. If we're checking if car is null, that's going to be okay. So let's have a look. So in here, we're going to have struct email car equals whatever the email folder variable is. Arrow emails, that's our head. And yeah, that could be null. But because we're traversing and we don't want to stop at the last one like we sometimes do, like if we're inserting at the tail, we've got to stop at that last node. If we're searching or printing, we want to include that last node in the loop, and we stop when we get to null. So we can say while car is not equal to null, and then check each node as we go along, right? And have a loop that's sort of like this, car equals car. And in this case, if car is equal to null, like at the beginning, this loop's just not going to run. Okay, but it's not going to crash anything. All right, how do we check if we found something though? What we kind of want to do is we want to keep searching while we're not at the end of the list and while we have not found the subject we're looking for in that node, right? That's like looking at the data inside the node and comparing it. Oh, we want to stop. We want to keep going, while we don't have a matching subject. And if these were integer values, this would be fine, but they're strings. How do we compare strings? The contents of strings. Yep. Yes, string compare. I'll just, answering so many, which actually is awesome, so thank you. String compare. So I'm going to have to say, let's use string compare for these two things. And actually, if string compare returns 0, that means they're the same. We want to keep going while they're not the same, like there's not a match yet. We want to keep searching. Now, by the end of that loop, either there was a match and car is pointing to some email, or there wasn't a match and car equals null. Either way, we're just returning car. And whoever's using it can work out whether it was null or whether it wasn't null. If it's not null, they've got a pointer to this whole node. They can access any of the other information they're interested in. So we just return car. Does that sort of make sense? We've done a traversal, we're returning a pointer to what we found, or null if we didn't find it. Now again, what on earth is going on here with this program, this test program? Okay, we've already looked at all that. Okay, so first of all, it was looking through the email list for a subject. Yeah, these were very creative. AAA. And it found one. And by getting that node returned, it was able to print out all the information about the email. It looked for DDD. That worked. It looked for EEE. That worked. It looked for holiday. That didn't exist. And it's printing out email is null. In real life, you'd print out something nice that a user would understand. You don't print out things about null to customers. All right, not on purpose. Then, all right, creating folder 2. This is just creating another folder with names in there as well. All right. How are we all going? Are our brains tired? Mine is. Right, so our choices are, so we've done what I labeled stage 1. We can talk about clearing folders, or we can do a Kahoot and talk about clearing folders and deleting emails, I should say, tomorrow. Hands up for Kahoot. Hands up for coding. There's no hands up for coding. All right, we'll do a Kahoot. All right, just give me a little chance to set it up. But we will continue this tomorrow, as well as talking about exam details and starting exam revision tomorrow. So get your devices ready and your brains ready. Give them a few seconds break. So yeah, I'll just wait a few minutes for people to join. Hopefully I'm not blasting people at home with this music, because we can't hear it loud here, but I don't know if the connection to the... Okay. I don't think we can hear it much at all. I'm not sure why. I don't know if we want to hear it, but... Okay, I'll just wait another minute or so. This is linked list, by the way, this quiz. Actually, I should probably start now. Is anyone still trying to connect? Because I think we're running out of time. All right, let's go. Apologies if you didn't connect in time. Is this the right one? Oh, very good. So yeah, only if we're deleting something, basically, are we going to freeze something. But that includes at the end. So that includes when we've finished our linked list, to make sure we don't have memory leaks, we should always delete any remaining nodes or clear the memory from any remaining nodes. Okay. Yes. Okay. No. So sometimes you might do it by accident, because if you've got a big program, you might have done it in this function and now you're doing it again. It's basically like using that memory again. In a way, it's going to crash the program. Oh, this is tricky. The X at the end means null. It's not an element. So this required some very good sight reading. Does anyone like play the piano or something and they can sight read well with piano music? Yeah, you get better at sight reading with code as well. I'm better at sight reading code than piano music or music. All right. What's happening here though? What in words is this chunk of code doing? Oh, it's a bad color. What's that doing?
Traversing through the second node.
Exactly. This is traversing through the second list and it's stopping at that last node. So it's going until the current 2 next is equal to null and stopping. So it's going to be pointing to the last node in that second list. And then it's connecting it to the first node in the first list. And yeah, that's a way of appending one list to another. That's not uncommon to do. So yeah, it should have 6, 7, 8, 3, 4, 5. Was that the correct answer? Good. Excellent if you work that out in like 45 seconds or however much time you had. Okay. Yeah, that's right. So this should actually work. And if you weren't checking for memory leaks, it might just work and seem fine. But it's going to have memory leaks because if your list isn't null, it works fine if the list is null. But yeah, if you've got a list, and this is what we were doing before, and you say head, oh gosh, I'll bring this forward, I can't reach anymore. If you say head equals head next, you're moving that along, but you're not freeing this node. Okay? So if you're trying to delete it and get rid of it, you're not freeing that node. That would be a memory leak. You'd still end up with the right list connected up though. So well done, people who got that. Yeah, this one will have a runtime error. And this is, again, what we were kind of looking at the beginning. So, whatever, head. So if we free this, and then we say head equals head next, we're trying to access the next field inside this node that we've freed. So we're using memory we've freed. Right, this pointer here was part of that node that I just freed, and this is going to crash, unfortunately. Okay. Last question. Oh, shivers, I'm blocking this. Yeah, this is kind of like our folder in our emails, right? We've got some kind of struct that itself isn't really isn't a node, but it's got a pointer called first to a bunch of nodes. Yeah, so I'd say if this was called my list, I'd be looking for that first field, and that's the head of the list. Does that make sense? Buried in that struct. All right, that's it. It was just a quick little Kahoot today. So if you're in the room, feel free to go and get some chocolates. If we've got electric squid, mystical lark, and bright angelfish, who I think led the whole way. Are they anyone in here? Yay! Congratulations. Get chocolates. People who came 4th and 5th, get chocolates too. And I think that's it for today. Tomorrow, we'll be doing more coding with that application and talking about the exam. Okay, thanks everyone. Good luck with your assignment. Bye-bye.